Hi there. Today we're coding the original prototype for Minecraft from scratch. This video was sponsored by Brilliant. Before Alpha, before InfDev, and before Classic, there was RubyDung, which had a very different bird's eye perspective compared to modern Minecraft. Sitting between there is RD132211, the earliest version still playable through the Minecraft launcher. To play it, you just need to go to Settings, scroll down a little bit, and enable this option. We're going to walk through each field and method and run the program at different points along the way to see how the fundamentals of the lightweight Java game library come together to form the basis of Minecraft. If you want to follow along, make sure you have Java 8 installed and a decent IDE such as Eclipse or IntelliJ. If you're new to programming and want to learn the fundamentals or dive into more advanced topics, let me introduce you to the sponsor of this video. Programming Minecraft from scratch requires the same problem-solving skills I've been sharpening on Brilliant. If you learn how to think in code, it makes it easier to understand Minecraft source code, debug crashes, and do real problem solving. Brilliant helps you turn your curiosity into a deeper understanding of technologies you use every day. Instead of just giving you lectures or giant walls of text, Brilliant has a hands-on approach where you actively solve problems with visual and interactive challenges. This helps you turn abstract thoughts into concrete ideas. I recently started their Thinking in Code and Programming with Function courses, and I've already found gaps in my own knowledge which only encourages me to learn more. The concepts are broken down, and they really lead you into rediscovering the fundamentals yourself. Whether you're trying to understand how to structure your code better or wrap your head around more advanced concepts, you can learn at your ideal pace. Brilliant is crafted by an award-winning team of teachers, researchers, and professionals from MIT, Harvard, Stanford, Caltech, Google, and more. This video is sponsored by Brilliant. To learn for free on Brilliant for a full 30 days, go to brilliant.org/jason13, scan the QR code on screen, or click the link in the description. Brilliant is also giving the first 200 users to click 20% off of an annual premium subscription, giving you unlimited daily access to everything on Brilliant. Thank you to Brilliant for sponsoring this video. Let's start with the basic refactor to match the original project. Our package will be com.mojang.rubydung, and let's rename our main class to be rubydung as well. Let's point to the new group. We can change the version as well. The lightweight Java game library is available on Maven Central, so we can update dependencies. We're specifically using version 2.9.0. I'm developing on Windows, but you might also use Linux or OS X. Now we add a new plugin called application, add a new application block. This will point to our main class, and it also sets a library path for natives, which we need to configure. So we can define a new configuration, then set the dependencies for that configuration to be valid. And at the end, we modify a task to extract the natives, then we depend on that task to run the full application. Let's reload again. Now we have this new run task under application. We can run this, and we see hello world as expected. We'll continue using this task going forward. We're going to follow a common convention, and that's to make it so that our game runs on a dedicated thread. We'll begin with implementing runnable. So we have this run method that we add, and I'm adding a print line statement so we see when that runs. Now we can do new thread, then new rubydung, and do .start at the end. We'll run this again. Now we see hello world and thread ran. So when main is invoked, we create a new thread. This executes some work. Then we spawn a new thread, which is concurrent and can do its own work. And we could continue spawning new threads or doing other work, listening for events or other stuff after that. But the main point of doing this is so that everything for the game is running together in its own dedicated area. To start setting up our game, we typically have an init method, and this relies heavily on the lightweight Java game library. So it may throw some exceptions from that. So we're going to wrap this with a try and catch block. Do this.init here. Do this.init, then catch any exception. And we don't want to completely ignore this. You could do something like e.print stack trace, but another convention we can do is use a J option pane, and this will make a standard dialog box. Let's intentionally throw an error, and we see failed to start rubydung with a runtime exception. Now that we have our init method, we're going to call to display from OpenGL, from the .OpenGL package. We're going to do set display mode, then create a new display mode. In here we pass the width and height of the window that we want to create. So following the original project, this will be 124 by 768. And after this, we need to call to display.create. So if we try to run this as is, we do get a window that will pop up, but it closes instantly. So after the try block that calls to our init, we're going to start another try block. I'm going to copy the dialog box and change this a little bit. Inside of this, we're going to have a while loop. We're going to do while not display.isClose requested. So if we haven't pressed the X or no event has been thrown to close the window, then we shouldn't do anything. Let's try this. Now we get a window that stays open, but if we try to close it, well, it took forever to respond, and it's not doing the expected behavior of just closing instantly. So let's force close it. So inside of this loop, let's do display.update. Run it again. We get a window, but we can close it properly now. OpenGL has support for a lot of different primitives. We're going to start with some basic points, but for most of this, we're going to be using GL quads. Before we update our display, we need to describe everything we're rendering, as well as our camera perspective and some other basic setup. Let's start with the point at 0, 0 on screen and see what happens. It's kind of hard to see, but right above my mouse there's a tiny white dot, and we see this dot is centered on the window. So if this is 0, 0, we could assume that a positive x would move it to the right, and a positive y would move it upward. So with these points as xy coordinates, we have down, right, up, and then left. And you see we're doing 0.5, so this would be a -1 here, +1 here, +1 here, -1 here. So we could change these to 3-dimensional points, so we need 3 floats. I'm going to add 0 at the end, so we're not translating in the z-axis at all. Running this, we see the same result. So by convention, we typically set up the camera before this, and we're giving this an FOV of 70. So this is adjusting how wide or how acute our field of view is. We also have the aspect ratio, which is 4/3 in this instance. We need this so our points get translated properly from the 3-dimensional space of our viewport to our 2D screen. Otherwise, things might appear warped or stretched. After we set up our camera in the projection matrix mode, we would then reset the matrix for object transformations. So running this code as is, we don't see anything on screen anymore. Part of this is due to the clipping plane. So in our previous examples, we had a frustum, and then only things beyond this plane would begin to be rendered. We can simply add a call to move everything away from the camera. Now we see those same dots just pushed away from us. Let's remove the center point, and if we change the rendering mode to quads, we consume the 4 points, and a square gets rendered on screen. Let's change our coordinates to render a square instead, and immediately you'll notice it's not perfectly centered on screen anymore, and that's because of how we described our points. So if the origin is 0, 0, we have positive x and positive y. Before we begin drawing, let's just recenter everything on screen. Now we see our square or quad rendered in the center. Let's move all of this to our render method, add a different value here. So we tell OpenGL that we want to modify the projection matrix. Then we tell it the field of view, or how large the frustum should be. We give it the aspect ratio, so it doesn't render squashed or stretched. Then we define near and far clipping planes, so anything too close doesn't get rendered, and anything too far doesn't get rendered. Then we tell OpenGL we want to modify the model view matrix. We push it away from the camera. The load identity calls here, identity is a mathematical concept, essentially meaning the original version. We move everything away from the camera, then offset everything so it's rendered on center with our camera. Then we open a new quad rendering context, we define our square, and then end the context. Then after render, we're doing display.update. So if we can do a simple quad, then we can do a cube. This will be our back face, and then I'll fill in the other ones. We can define each point of the cube, and then it will consume 4 at a time to render a quad. But if we do that without any rotation, we're still just going to see a simple square on screen. We're going to track rotation with the float. After everything is rendered, we're going to increment the rotation. We're going to rotate before we offset back to the center. I made this non-static, and we're rotating on the X and Y planes. So running this, we get a really weird view. A weird shape gets drawn over time. Let me run it again. At the very beginning, you see the square, and then it forms this shape over time. So what's happening here is the screen is not being cleared before we're drawing the next frame. So at the very top of render, we're going to call it the GL clear, and we're going to clear the color buffer. Running this again, we get a cube that's rotating pretty fast, but we can't really distinguish the sides. Let's add some color by describing a new color before each set of vertices. So if we do this, it seems like there's a rendering issue, but it's actually OpenGL not trying to make any assumptions about what you're trying to do. If you don't tell it to not render things that should be hidden, or to not render the other side of a triangle, then it will do those things, and what we're seeing here is over-rendering, where the faces farthest from us are being rendered on top of the faces closest to us. So inside of init, after we create our display, we're going to tell OpenGL we want to use a clear depth of 1. We have our near and far clipping planes, so this would be 0, and then 1 would be the far clipping plane. Then we enable depth testing, so as something goes further, it tracks how far away from the camera it was. If the closest point is less than or equal to a point behind it, then we will render this front face instead. Inside of our render statement, let's also clear the depth buffer. Now we see it's rendering properly. One thing we might want to measure would be the FPS. How many frames are we actually rendering per second? So before we start this while loop, I'll put it outside this try block. We're going to get the current time and initialize a new frames variable. Then after we render, we're going to increment the frames, and then we can print FPS every second. We'll take out the chunk updates for now. Let's run it. And you see we're hitting over 2000 FPS for this very simple project. So from here I was debating on whether to do many cubes on screen first, or whether to texture the one cube, but I think it'll be interesting if we kind of do them both. The original tessellator class has support for vertices, textures, and colors. We hold a buffer of up to 100,000 vertices for any given frame. And remember that we're using quads, so we need 4 vertices to describe a quad. So in reality, we could also see this as 250,000 quads. Float buffers are literally just containers for numbers, and we need a set of 3 numbers together to describe a point in 3-dimensional space. So if we're tracking 100,000 vertices, then we'll have 300,000 numbers in that buffer. For textures, we use UV coordinates, so that's a pair of 2 numbers, so we have 200,000 numbers in the texture coordinate buffer. And for color, we track RGB, so again, 3 values, so that's 300,000 numbers. As we set our rendering calls, we might use color or texture data, so these values will be updated as we iterate over vertices, and these booleans are directly linked to each of those. We're going to go over each method here, starting from clear. So this resets our total vertices count and then clears all the buffers. Inside of init, we're calling to clear and setting has color and has texture to false. Text and color are pretty similar. They update the Boolean values to say that we're using that data and update the current values. Vertex should always be called after color and texture. So we check if we have that data and then insert the data if we need to. Otherwise, we just put a position into the vertex buffer. We increment the total amount of vertices that we're going to render, and then we call it a flush. This is the majority of the logic in this class. When we call it a flip, say that you have a stream of data and you're writing to different points along the way. When you're ready to read back that stream, your pointer would still be at the end. So what flip is doing is putting the pointer back to 0 and then setting the size to read the entire amount in between that. We give our vertex buffer to OpenGL and say that it uses a size of 3 for the coordinate there. So that would be for X, Y, Z. And if we're using texture or color data, we create pointers with the appropriate size there and give them the correct buffer as well. If we want to consume those buffers, we need to enable different states, such as GL vertex array, texture chord array, and color array. This tells OpenGL that we want to consume data from the buffers that we gave it earlier. GL draw arrays uses the buffer that we gave it to backdrawing with that buffer. We tell it that we're rendering quad, so it consumes 4 vertices at a time to render 1 quad. Then we give it the total amount of vertices to render. After we're done rendering in this context, we disable these client states. Then we call to clear to reset the buffers and the vertices count. So let's use our tessellator with the single cube we have right now. We're going to create a new tessellator at the top of our class. We want to update most of this. Before we begin drawing, we're going to reinitialize our tessellator. We're going to get rid of these begin and end statements. Now instead of these GL color 3F calls, we're going to replace those with t.color. And instead of these vertex 3F calls, we're going to replace those with t.vertex. We keep color data before vertex data. And at the end of this, we want to do t.flush to actually render it. Let's run this. And we have the exact same thing on screen, which is what we're expecting. This is good. Let's take this actual drawing logic for one cube. We're going to extract it to its own method. This will be draw single cube. And we're going to reuse this method to draw multiple cubes on screen. So even though we're describing the exact same vertexes, we can translate the model view matrix and make cubes appear at different locations. We're going to start with 100 cubes. We're going to use 3 different float arrays to track the X, Y, and Z positions. We need to initialize those new positions, and we'll do that in our init method. We're going to update our rotation real quick. We're going to make sure it wraps at 360, so that would be 1 full rotation since we're using degrees. I'm also creating a value for cube size so we can adjust how large the cubes are. We're going to replace draw single cube and reuse it in draw cubes, which we'll call here. We need to make sure to use the cube size and draw single cube so we draw cubes of the appropriate size. So let's step through what's happening here. Obviously, we're iterating over the total amount of cubes. So this could be 100, 1,000, 2 million, however many we want to render or keep a track of. The push and pop calls are pretty much the most important thing here. So we did a bunch of stuff before this. We're going to do stuff after this. But in the middle, say that on our screen, the current context we're rendering from would still be the center, okay? What we're going to do is save the current matrix. So say that we're saving this as X, Y, Z. We perform a translation, or in this case, we perform 2 to recenter it. So we end up in a new position, and we'll call this XYZ prime. Then we draw at that position. So we draw our cube from that context as if it was an origin point. And so nothing else gets rendered weird. We reset the origin point to 0, or wherever the context was at originally, if we had something more complex going on. So we implemented the tessellator, and we were able to draw a single cube if we wanted to that was still rotating perfectly fine. Now we're going to attempt to draw 100 cubes. We're going to track position in 3-dimensional space for each of those cubes. Those positions are initialized at random at the end of our init method. And then during our render method, we clear the screen, we set up our camera, set up our object translations, and rotate the entire scene. And then we call it the draw cubes, which should be drawing multiple cubes at different positions based on a translation. So let's run this code as is. Now we're in the middle of a bunch of cubes. We're still hitting about 2,000 frames per second and going over that sometimes. So if we want to visualize this better and have a better understanding of which faces we're actually seeing, we can look at normal maps, which are pretty much the direction that each face is facing. So if something is facing upwards and we're talking about 3 dimensions, then its normal would be 0, 1, 0. If we use that same value as an RGB color, then that color would just be green. So let's revisit draw single cube, and we're going to put the normals into each of the color statements. So one issue we have is that color is 0 to 1, but a normal might be -1 to 1. So we're measuring 3 values, RGB. Say we're doing the bottom face, then we would have 0, -1, 0, because the face would be pointing downwards. So this would be its lowest value at G. We'll have 0 instead of -1. We're going to set the other values to 0.5, just to give it a little bit of color. All right, let's run this. Now you can see the fronts are blue, the tops are green, we have yellow backs. Let's freeze frame. The normals that we calculated are from the cube's perspective. So the front being blue means that any way this thing is facing, even if it's all the way off to the right, that would still be the front of the cube. But to us, as this rotates and starts facing towards the right or some other direction, then from the camera's perspective, it's facing a completely different direction than the cube itself thinks it is. We calculated the normals of each face. Now we're going to get the average of which direction the camera thinks the cube is facing, and then update the colors based on that. I'm going to have this article linked. One of the first things we need to do is create a buffer with size 16 to hold this matrix, and ours is rotated slightly. Ours is in column major order, this is in row major order, and as this says, this represents rotation and scale and translations of an object. We're going to pass in the model view matrix later, along with the normal vectors of each side. We're taking the rotation and scaling, so only that upper 3x3, getting the average as new normal vectors, adding those all together, and creating a new color out of the initial normal vector and those new normal vectors normalized. So instead of all of these weird calls, we're just going to fill in the normal vector for each of those and pass the model view buffer. So before I replace all those, we're going to make sure to clear the buffer before each rendering, and then get the model view matrix again and pass that into the buffer. Now we update each of those colors and run it again. You can see as the cubes rotate, the colors begin to shift slightly. So this green shifts to a cyan, shifts to a light blue. So instead of the face being purely green, it's now the average of that green along with the slight rotation. Let's change the clear color of the background. Now we're going to bring in the only resource for this game, which is the texture file. I've modified the texture slightly to avoid copyright issues, and we're going to go over the textures class. Start with a map of file names to integer IDs. We set an arbitrary ID as our first one, so we can always bind a new texture at the beginning. If we're attempting to load a texture, we see if our map contains it first. If it does, then we return that. Then we'll return the integer ID of the texture. We're going to bind the texture and make sure we either do or don't overflow based on the mode that's passed in later. We get the image as a resource stream, which is basically just retrieving it from its internal location. We get the width and height. We create a buffer to hold the ARGB data at each pixel, so the coloring and the transparency of it. We get the raw data starting from 0, 0 with no offset. So Java typically uses this format, just ARGB or alpha first, then the RGB value for the color. Most GPUs, or at least OpenGL specification, depends on this RGBA format where the alpha is at the end instead. But as I copy and paste it from my notes, we're actually storing this in reverse order because it's read with little endianness. So the least significant digits are read first. So it'll read R at the end, then G, B, A. We copy over the pixel data, then give it to the GPU so we can reuse the texture later. We're going to track the integer ID of our texture at the top. GL nearest meaning if we're sampling a specific pixel, it'll return the closest pixel color, which would be within the boundary of the texture. We can actually put this as -1 for now, and then later in our init method, after our display is created, we can load the texture. Then we'll bind the texture with that ID. Later, inside of draw cubes and draw a single cube, we'll enable texture 2D and bind our texture. We need to get the UV coordinates. We have a 256 by 256 pixel image. Each texture we have is 16 by 16 pixels. So we're going to start at 0, 0 and go to 16, 16. Just like we define a quad with 4 distinct points, we also grab the texture with those 4 distinct points as well. Let's run it as is. And what you're seeing right now is the normal colors interacting with the texture as well. Let's set all the colors to 1. Now we see everything's grass. And so we have all these cubes, all these random points in 3D space being rendered as a texture cube in the world. But that's not Minecraft. We need a solid level that's broken into discrete chunks. If something's outside of our viewpoint, we also don't want to render those chunks. Okay, brief intermission. Say we have a camera that is viewing level all the way up there. So far we've rendered a bunch of cubes everywhere. So in this version, we're going to go from blocks to a level which holds an array of discrete blocks. So in a moment, we're going to redescribe a block, and we're going to call it a tile. Then our level is going to hold an array of tiles or blocks. So we'd start at 0, 1, 2, and we could index each individual block in the world. I'm going to move this over. So when we're actually going to render, we only want to take out specific portions of this, and we want to see if that portion is actually within our view box. So anything outside of our frustum, then we wouldn't render that chunk. So we're going to start with individual tiles, then tie that into a level, and then break level into discrete chunks for rendering. Tiles are extremely basic. They track a single integer for the texture ID. Tile has 2 methods, but for now we're only going to implement render face. And so we're given a coordinate in 3D space, along with a tessellator, and a number to represent the face that we'll render. We'll create 2 pairs of 3 floats to track the 2 corners of a cube. So we would have 0, 0, 0 and 1, 1, 1. And very similar to our rendering logic earlier, we're going to give our tessellator some vertex coordinates. We're using 0 to represent the bottom face. So you could examine these coordinates against a cube to see how it defines the 4 bottom vertices. And we'll do the same for the other faces as well. So we're doing bottom, top, north, south, west, then east. At the top of this class, we'll define public tiles so that we can reuse rock or grass and then call to render face on those. Let's get rid of draw cubes for now. I'm going to do tile.rock.renderface and pass it the tessellator and pass it 0, 0, 0, and 0 for the bottom face. Let's try to render the other faces. Let's wrap this with t.init and t.flush. Now we're back to a plain white cube because we're not passing color data or texture data. So notice how we're only passing vertex data. So there's no coloring, no texture going on. And what this represents is the block highlighting. So when you're looking at a block, it lights up. Let's do the rendering for a single tile now, but we still haven't defined level. We start with the UV coordinates of the texture. We use the coloring as brightness. So as you saw, if we set a color to entirely 1, it's white or a fully bright block. Just like we did for the first cube, we're using fake directional lighting. We collect our coordinates for the nearest and farthest point of the cube. And remember that we were supposed to have a level here. So we have some skeleton code that I've commented out. We have these values as true for the different faces that we're rendering, and I'm using full brightness at 1.0 instead of getting it from the level. Layers refers to display list from OpenGL. So you might have heard of a VBO before, a vertex buffer object. A display list is not a vertex buffer object, but they are related. So instead of recalculating our vertexes every frame and flushing the buffer, if the player's not moving or the world's not changing, then we don't need to recalculate, a display list basically being a compiled frame that we can reuse immediately. So instead of render face here, we're going to do render. We need to modify some of the arguments, so it doesn't take a face at the end, but it does take an extra number for a layer. So let's take off the numbers at the end, just add an extra 0. Let's run this as is. Now that's kind of weird. We see 2 distinct faces being rendered. Let's run this again. So we start with nothing. We see the top face come into view, and it's rendered. As the cube rotates, we don't see the top face anymore. We see the back face come into view. We shouldn't be calling this so many times, that's one thing. If we set the layer to 1, then we see the sides are rendered fully white instead, and the top and the bottom are now transparent. Part of this is due to the bitwise XOR here. We also have this BR equals C1, so we have the C1 values here for a fully bright block or a slightly tinted side. We were seeing the top face first a moment ago. This is true, so we can ignore that. We have a brightness of 1, and C1 is also 1, so this is always true, which is also just a 1, and we could put zeros before that if we wanted to. We're calling to this with a layer value of 0, so this statement would return false, which we could also just see as a 0. So if we're taking the exclusive OR of 1 and 0, then our output will be true, or a 1. So that causes the top face to render on layer 0. For the north face, layer is 0, which is not equal to 1, so we have 0. I have brightness hard-coded to 1.0. C2 is 0.8, so this is also false, or 0. If we take the exclusive OR of 0 and 0, we see the output is 0, which we could also see as false, and so none of this logic occurs. So once we have level implemented, this will be a little more obvious what it's doing. The level is solid tile. If there's another cube blocking this face, then obviously we shouldn't render that face. So after that, we get the brightness. So the brightness is determined by other blocks obstructing the skylight. If we had a block way up here, then light won't be able to reach that next block, and so it applies a shadow, and we would use a lower value instead. Under normal conditions though, if a block has access to the skylight, then we render the top of the block with full brightness. We render the sides slightly darker, and the bottom we would consider in shadow, so we render it a bit darker. We're going to have 2 display lists, each of those working on a separate layer. Layer 0 handles full brightness blocks. Layer 1 is going to handle blocks that have the skylight obstructed by other blocks. So you could think of this as clear versus shadow. So if the brightness of this face matches the expected brightness if we're being hit by a skylight, then we continue to render. Otherwise, if we're rendering a face that's in shadow, then we'll continue to render as well. So we could just call to render with both layers. We run this code, and we see a grass block. So let's compare our texture. We have grass first, and then cobblestone. But here we have rock as 0, and then grass as 1. This is a bug that's actually present in the original game. So we could just swap these and run it again. And now we have a cobblestone block. But we're going to leave this as it is for now, and we're going to revisit this. Let's make a few changes. I added this finally block down here at the end of our try catch for rendering, and we need to destroy the display to free the memory that's taken by OpenGL, and this will only happen after our display is closed. Let's also get rid of the rotation for now. In the original game, we're not rotating the entire scene, so we're going to get rid of most of this for now as well. Clean up our init, take out the rotation statement. I'm going to comment out draw cubes for now. We can get rid of set normal color. So clean up the code a bit. Now we have a static cube on screen. It's not doing much. What I want to do next is enable some keyboard and mouse input, so we can move the camera around, look around the cube a little bit. Then we'll get into breaking down the level renderer, chunk, and then frustum culling as well. So we have a cube in the world. Right now we have a stationary camera. So all we're seeing is one face of it. We're just seeing a square. So we want to be able to track the position of the camera, be able to move it however we want to, such as rotating or translating it. And if the camera moves to a new position, then we should update the display as well. So we track the current position. This is for where we're currently at in the world. We also want to know where we're coming from, our previous position, and we need to know how fast we're moving, the delta or rate of change of our movement. We'll also track rotation on the Y and X axis. We'll go over bounding boxes later. For now, we have a method called setPosition, which sets our position to a new position. We have a method called turn for setting our y and x rotation. We have move relative, and you'll see these sine and cosine functions based on our rotation on the y-axis. We also have a move method, which is pretty dependent on bounding boxes as a whole. So this handles our collision checks. So you can see how it uses clip y collide, clip x collide, clip z collide. For now, we're using it to reset our movement to 0. Most of the logic is going to happen in this tick method. We'll add the method for resetting our position later. I'm going to comment this out for now. We're going to adjust some of this. At the top of tick, we're setting our old position to our current position. We explicitly set the x and y acceleration to 0. We're specifically setting the x and y acceleration to 0, so then if we press certain keys, it'll increment or decrement them based on that. That would range from a 0 to a -1 or a +1. So you can see we're able to use W, A, S, and D, or the arrow keys. The spacebar handles jumping, or upwards movement. Now let's go back a moment. W and S are affecting our y values. So what is going on here? We have a bird's eye view to the top of a square. So this is the top of the square. It's not the front side, this is the top, okay? So this is the same perspective that we see a level or a chunk from. So from this perspective, we have x as our horizontal coordinate, and we have y as this vertical coordinate. So we're essentially seeing this as a 2D image. Now, the problem comes when you're used to modern Minecraft's x, y, z coordinates. So it's a bit switched around from the modern system, and our z would actually be the depth that we go deeper into the world. We apply our actual movement, we set the player to a new instance at the bottom of our init method, then we use keyboard create and mouse create to have singleton references. We'll make sure to destroy those references. We're going to go over a few methods. So we have move camera to player. We're going based on the original project, so we move everything away from the player slightly. We apply the rotation. Instead of the constant rotation we had earlier, we're going to use the player's rotation instead. So that'll be the x rotation on the x-axis and the y rotation on the y-axis. We interpolate between frames, and so we're going to go over adding the timer class in a moment. We move the entire world. The camera is essentially staying at the origin while we translate the entire scene around the player. Let's go over adding the timer and what this A value means. We're going to recreate the timer class from the original project and also helps for interpolation between frames. We're going to start with 3 fields. So there are 1 billion nanoseconds in a second. We're going to have 1 billion nanoseconds max per update, and then we want to process 100 ticks per update. We're going to track how many ticks we should process. And then we have a poorly named variable, just named A. This is essentially the measurement of an average between 2 frames from 0.0 to 1.0. So you might know this in future versions of Minecraft as a partial tick. We have a timescale for measuring whether we're going to slow down or speed up the gameplay, which we're not doing in this. We have a float for tracking the current FPS. We track the amount of time passed between ticks. We measure how many ticks are happening within a second, and we keep track of the last time the timer was updated. We have a simple constructor, which takes the float of ticks per second, or how many ticks to process per second, and we set last time to the time that the timer was created. The rest of this class is all in one function called advanced time. We calculate the time since the last call to this method. We update that last time value. If the clock gets adjusted, or we need to wrap around, then we set back to 0 instead of using a negative time. We clamp the amount of time passed to 1 second so we don't see huge leaps in rendering. We're going to calculate the instantaneous FPS, so this is billion over the time it took for a frame to render. Here we're actually just accumulating the total amount of ticks. We're going to cap that off at 100. Then we keep any leftover ticks that we still need to process for the next frame. Then we set the partial tick value to the past time. Like I said, this is interpolation between 2 frames ranging from 0 to 1. So at 0, you would still be rendering the previous tick, and at 1, you would be rendering the current tick. We're going to implement pretty much the entire usage of timer now. In this original version, it was actually set to 60 ticks per second compared to modern Minecraft's 20 ticks per second. In our run method, before we render anything, we're going to advance the time, and we need a new tick method, which for now isn't going to do anything. We're going to briefly touch on AABB, or axis aligned bounding boxes. Even though the player is invisible, we still want to be able to collide with boxes, and these bounding boxes are used in other places as well. We start with 2 pairs of 3 coordinates, so that's the bottom left closest corner and the farthest top right corner. And epsilon is basically the smallest unit that we can ignore, so this would be 10 to the power of -7. In the original decompilation that I have, even checking against the bytecode, it was just using 0.0 outright, so I did modify this. We construct a bounding box with 2 sets of 3 points. We have an expand method, which takes 3 parameters, so you can optionally expand on any axis. So if we passed +1 for the x-axis, this would grow the right face outwards to the right, and the rest of this would remain unchanged. Grow is very similar. We can grow in any axis. When we look at grow, we're doing this +x. We're going to grow the same on each side. We would subtract a +1 and add a +1. So rather than taking the average and splitting that in half, it grows that amount on both sides. Move is also pretty basic, and you move each position of the bounding box to a new location. The 3 methods for clipping are pretty similar. We check if the y coordinates are in the same range, then we check if the z coordinates are in the same range, then also see if the x coordinates are in the same range. And it's very similar for y and z planes. Intersects is a much more stripped down version of that exact same thing. Is my lowest position overlapping your max position? Is my max position overlapping your lowest position? We'll look at the entirety of expand for a moment. Moving is pretty straightforward and just offsets by those values. We're going to describe a bounding box for the player. This on-ground boolean will be used later. In our constructor, we'll create a temporary bounding box. Typically, this is set using set pause or reset pause, but we still haven't implemented level, so we'll do that later. And we don't have collision checks just yet because we don't have a level, so I'm setting this as a new list, but we're still going to move the player's bounding box. The original value is not equal to the current value, and we'll set our delta movement to 0, as those values get updated with collision checks. We store the movement as originals, then we update the values we received if we were colliding, and we move the bounding box around based on those. These values would only change if we intersected with the bounding box, so we set these to 0 to prevent movement if we were colliding with something. And then we set the player's position to the center of the bounding box. We move the eye position midway from the bottom of the bounding box to the top. So we have a player that begins as null, and we initialize a new timer at 60 ticks per second. Our new thread starts, we go to initialize, our display, keyboard, and mouse instances are created. We bind our texture, enable culling. Down near the bottom, we create our new player instance. We continue on to advance our timer, and then call to tick, which calls to tick on our player. We render with interpolation based on our timer. This handles getting the motion of our mouse, turning the player, and moving the camera to the player's position. Then we get set up for rendering, and we render some tiles. Now we have a prototype that could easily turn into a 3D flappy cube clone. There's still no collision, so we can follow directly through this. Let's play around a bit. We're going to add a new bounding box to this list, and we'll make a cube at position 0, 0, 0. We're going to uncomment our collision checks, and then run this code as is. Let's try and bounce up and get on top of it. Now we have collision on a single block in the world. Now I need to apologize, and I want to make this outro as short as possible. There's still so much to go over. If we pull over the original project, we still have chunk, frustum, level, level listener, level renderer, hit result, and the implementations of those in the different classes. We're going over 30 minutes now, and as I was making this video, I did try to get a lot of feedback. In the original video, I edited out a lot, I skipped a lot of explanations, and it was only about 20 minutes long. But we did create the entire project in that time, but it was nowhere as in-depth as this video was. Now, we only have the very basics, so I'll count this as like a part 1 if anybody wants a continuation of this. But that's the reason for the title, is I don't have the time to do this. I originally started filming for this video 10 days ago, and in the process, I had to restart multiple times. I used to use CapCut, which has had its own issues, and I lost a decent amount of progress due to that. So I want to end with a huge thank you to Ofek. He helped me break down this project a lot, and he also provided me with a decompilation that I based this video off of. So I restarted a lot. It took me a while to get some of the explanations right and actually correct some of my information. And as I've stated in previous videos, I'm a very junior developer, man. I'm like winging it right now, but I really do hope you enjoyed this. If you want to see a part 2, please let me know. I also want to thank the channel members and thank Brilliant one more time for sponsoring this video. Without you guys, I can't do content like this, especially not this long of a video. So I do appreciate it. Thank you to everyone who views this, and make sure to subscribe for more.